So to determine critical load, we have methods using neutral equilibrium. Method of neutral equilibrium to determine critical load. So another method that we can use is we use the behavior of imperfect column. We do analysis and we give the structures or the model of the structures some imperfections in the shape. We make it not perfectly straight, not perfectly horizontal. We make the structures model imperfect, and we make use of the criteria. When you apply loading, when some deflections in the building model suddenly increase a lot, so we use that loading as to approximate critical load. Okay. So that is the method that we have gone through. Now there is another method that we want to look at. The other method that we want to look at is the method using slope deflection equations. So this is the next part that I would like to go through. And this slope deflection equations is given in this particular notes that I share with you, section 3.4. In section 3.4 is effect of axial load on bending stiffness. And this is specifically by looking at the slope deflection equations. Now, slope deflection equations as shown on this slide. I think slope deflection equations in this particular topic, we want to derive these equations and make use of these equations to solve a given problem to determine critical loads of that column or the frame, okay, or members in the frame. And these equations here is relating the end moment at both ends here to the end rotations at both ends. So that set of equations is given by these two equations as shown here. So end moment MA, as you can see in this diagram, MA is equal to EI, which is a flexural rigidity of the member, divided by L, which is the length of the member. Then multiply in this bracket here, another symbol that we introduce here, alpha N, multiply with theta A. Theta A is the end rotation at this end, plus another coefficient alpha F, multiply with theta B. This is for MA. Then for MB, which is the end moment at the other end there. So MB is equal to, again, EI over L. Then in bracket, multiply with alpha F, theta A, plus alpha N, theta B. So what is alpha N? What is alpha F? What is alpha F and alpha N here? We will look at later. This is a kind of coefficients which we need to, which is affected by the ratio of P over P critical. So this alpha N, alpha S is a coefficient which is a stiffness coefficients. And these are stiffness coefficients which are affected, which is a function of P over P critical. So this slope deflection equations is different from the slope deflection equations that we normally encounter. We normally use for beam analysis. For beam analysis, we have beam analysis, the slope deflection equation is simply EI over L for beam, 4 theta A plus 2 theta B. And for MB is EI over L, 4 theta B plus 2 theta A. This is for the case of beam. Without P. Yeah, there's no P. So when we compare this equation and this equation with P and without P, okay, with P, yeah, this is consider the effect of P. This is without P, when P is equal to 0. So the normal one that we have learned, and then we have made use of this slope deflection equation in the solving of statically indeterminate problems is given by this set of two equations. And it is this, whatever we multiply with theta A and theta B, the coefficient here, they are constant. 4 and 2, 2 and 4 here. This is when P is equal to 0. But when the P action of the P, effect of the P has to be considered because it has effect on the bending stiffness, then this alpha become a function of P is not constant anymore. It's not constant anymore. So that is one of the difference of the slope deflection equations, where the conventional one and the one that we need to consider the effect of P. So we are going to look at how these equations are being derived. Okay? The derivation process is a bit lengthy, but we will just go through how the equations is being derived. Okay? And for slope deflection equations, we derive, we look at the derivations for two different cases. Okay, the first one is without relative lateral translation of member ends, which is this member and this member, they do not translate relative to each other. And we derive the equation first, which is this. Okay. Next, we derive the equations for slope deflection equations with relative lateral translation of member ends, where this member end translate relatively to this end. Then finally, we combine these two to get the general slope deflection equations for the case where you have n rotation, at the same time you have n translations. So this is n translations without n rotation. So rotation here 0, rotation here 0. And this is the case where the n translation is 0, but the n rotation is not 0. For the purpose of derivation, we separate them first, but later they can be easily combined to get the final slope deflection equations. Now, slope deflection equations is relating the n moment, the n rotation to n moment. Again, when we consider P, then this coefficients here, alpha n, alpha f, is not constant anymore, but is a function of P over P critical. And what is alpha n and alpha f? This next slide shows alpha n and alpha f is given by these equations here, which is pi n over pi n square minus pi f square. And pi alpha f is pi f over pi n square minus pi f square. And later we can see where do they come from. And pi n and pi f are a fairly complicated form, which is given by this equation and these equations, where k is given by this equation, which we normally use it very often. K square is P over EI, or K square is P over EI, or K is the square root of P over EI. So we have used this, we have seen this many times, okay? So these equations, of course, when you are asked to solve this equation will be given to you, or you can refer to reference, because these equations are fairly complicated and no need to remember them, okay? Then this is for the case without n translations, without relative n translations. Then when there is n translations, we have extra terms appear, which is this. We have extra terms appear, which is this. Okay. When we have n translations, it causes additional n moment. Okay, and through the derivations, we can prove that additional n moment is equal for both n and this n here. Then they are given by this equation here, minus alpha n plus alpha f delta over L. Delta is a relative n translation. L is the length of that method. So this set of equations is the equation that we need to use when we want to solve a problem to determine critical load using slope deflection equations. If there is no n rotations, then this term disappears. If theta A and theta B 0, then this term will appear. And if there is no n translations, if delta equal to 0, no n translation means delta equal to 0, so this last term will disappear. But if the problem that we consider have both n translations and n rotation and n translation, then this and this both terms will not disappear. So we will see how this equation are being used later on when we try to look at application of this slope deflection equation method to determine critical load. Now, KL here, this alpha n and alpha f is a kind of coefficients which will affect the stiffness. So it's a measure of bending stiffness. Now, EI over L is a kind of bending stiffness, and multiplied with alpha n. Here, EI over L will be multiplied with alpha n. EI over L will be multiplied with alpha f. So this alpha n and alpha f, which is multiplied with EI over L, is a kind of coefficient which will affect the bending stiffness. Okay. This EI over L is a bending stiffness and multiplied with alpha n. So this alpha n is a coefficient multiplied on bending stiffness. It will affect the bending stiffness of the member because of the why? Because of the effect of this extra load P. And this alpha n and alpha f, if you look at the detailed equations here, alpha n, alpha f, detailed equation here is a function of KL. It's a function of KL. Okay. So this bending stiffness coefficient is a function of KL. Okay. And KL, this KL here, okay, it can be further rewritten into this form, which is KL is equal to pi P over P critical, or P over P Euler. So actually alpha n and alpha f is a function of this ratio. So alpha n and alpha f is a function of P over P critical, or in this case we use P Euler because it is considered as both and pin conditions. And this graph here, which we plot alpha n here versus KL. Okay. So we look at the case, okay, alpha n versus KL. We look at the case of theta A not equal to 0, theta B equal to 0, delta over L equal to 0. We look at the case of a member where theta B is equal to 0, and then delta L is equal to 0, means there's no n translations, and we try to plot the alpha n in that case, okay, versus KL. Now, if you look at this graph here, as P increases, a horizontal axis, P will increase. As P increase, alpha n will decrease until alpha n becomes 0. Now, the meaning of P increase means, I think when you have a slope deflection equations, when you have a member here, then this P increase. So from this graph here, when this P increase, but the important is relative to P Euler or relative to P critical, relative to this, when this one increase, which means when the value of P acting in this member become larger, okay, then alpha n will decrease. It starts with 4. That is when axial force is equal to 0. This is the coefficients that we use in the normal slope deflection equation method, 4. But when P increases, then it starts to be less than 4. But in the beginning, when KL is still within this 0 to 1, okay, so it is almost equal to 4. So the effect of this P on the bending stiffness is very small. But when P increases beyond this, increasing more and more, then it starts to have effect on the bending stiffness. And when P is equal to P critical, this is the point when P is equal to P Euler, which is the load that you apply is already approaching or exactly equal to the critical load of that member with the pin-pin conditions, then we get stiffness 0. Okay. So when the load that we apply relative to P critical is getting larger, it has effect on the bending stiffness. That is, it decreases, it will reduce the bending stiffness. And at the moment when at the instant when P is equal to P critical, you get 0 stiffness. Stiffness vanishes, you get 0 stiffness when P is equal to P critical. So this is the meaning of this graph here. So the important thing that we can get from this graph is that the ratio of P over PE will cause a reduction in bending stiffness. In the beginning, when this is small, it will not affect so much. When it's getting larger, the P over PE ratio, it will be affecting more and more on the bending stiffness, reducing it more until it becomes 0 when P is equal to P critical. So from this case here, we can use the criteria. We can have a criteria for P critical. So one of the criteria for P critical is the axial load that will cause the bending stiffness of a member to become 0, as shown in this graph here. So we can have another criteria to determine P critical, which is the load level P that will cause the bending stiffness to become 0. Now, this is another graph to show the alpha n and alpha f. Okay, so one of this is alpha n, and this is alpha f. Okay, and this is when the load applied is in compression, and which is when the load applied is in tension. So we will not consider this. We look at this solid line here. So here, we're trying to show that when KL is less than about 1 or P over PE is less than about 0.1, there is little change in the value of stability functions. So this is actually alpha n, this is alpha f, right? Which are close to 4 and 2. So when they are getting larger than certain values, so that it start to have effect on the this bending stiffness. Okay, so class, I think I will stop here, and when I meet you again on Thursday, we will go through very briefly the derivation process of these slope deflection equations, considering the presence of the effect of axial load, okay, which is we will go through section 3.4, a bit of the derivations, okay, and also then we go to the applications.